Hi everyone, welcome to the second tutorial. Okay, so the agenda for this tutorial is to continue with the exercises that we are doing in our last tutorial. Okay, so let's proceed with question 49. We already ran question 47, 46 to 48 in our first tutorial. Okay, so here is the question. Show that if x is a real number, then x minus 1 is strictly less than to the floor of x, which is less than equals to x, which is again less than equals to the ceiling of x, which is strictly less than to x plus 1. Okay, so we know that we can write x as n plus epsilon, right? Where n is an integer and epsilon is between 0 and 1. Okay, so since we are writing x as n plus epsilon, it means that n must be less than or equals to x, right? For example, if I have 1.78 x and I'm writing this x as n plus epsilon, integer plus some decimal part. So n is 1 plus epsilon is 0.8. So this n must be less than or equals to x. Inequality occurs when x is integer itself. Okay. So this means we can also write x. We can also write x as x equals floor of x plus epsilon, because we know that the floor of a number x is defined as the greatest least integer of x, right? Okay, so and here again epsilon is between 0 and 1, right? So this is by definition of the floor function, because we know that the floor of a function is defined as the smallest integer, like if this is x, so this is the floor of x. So the greatest integer which is less than all the integer which is less than x. From all these least integer, we choose the greatest one which is less than or equals to x. Okay, now since our epsilon is in between 0 and 1, right? And from this equation, we can write epsilon as x minus floor of x. Okay, it means we can replace epsilon by this term. This implies that 0 is less than equal x minus floor of x, and at the same time this x minus floor of x is less than 1. Okay, right. So what it gives us, that floor of x is less than equals to x, and x minus 1 uh, x minus 1 is less than floor of x. Okay, so by combining these two, this implies that x minus 1 strictly less than floor of x, and this thing x is greater than the floor of x too, right? So this is greater, x is greater than equals to x. So by combining these two, we can write these two inequalities like this. Okay, so let's call it equation 1. Okay, so as we see that we can write x as this, right? In the same way, we can write x and we can also write x as x equals floor of x minus a number epsilon, right? Because we know that floor of x, this is x, so the floor of x lie here, is the least integer from all greatest integer, which are greater than or equals to x. Okay, and here epsilon is in between 0 and 1, 2. Okay, since again epsilon is between 0 and 1, we can write epsilon as x minus ceiling of x minus x, okay, less than 1. And this thing implies that 0 is less than to this factor, and at the same time this thing is less than 1, 2, right? So this thing gives us x is less than equals ceiling of x, and this one gives us x is less than 1 plus x. So by combining these two, what we get is x is less than ceiling of x, which is again less than 1 plus x, namely the equation 2. Okay, so by combining 1 and 2, what we get? x minus 1 less than, right? So we are combining these two equations. X minus 1 less than floor of x, which is less than equals to x. Now this x is k less than equal to ceiling of x, which is strictly less than 1 plus, right? So this parts come from equation 1, and again this parts come from equation 1, and this one comes from equation 2, which is nothing but our desired identity. Okay, now let's go to our next question, which is question 50. Okay, so question 50 tell us that show that if x is a real number, so x belongs to real number R, and m is an integer, m belongs to an integer set, then the ceiling of x plus m is equivalent to x plus this integer m. Okay. First of all, again, we can write x as n minus epsilon this time, right? So we have a choice always that in what form we want to write Rx. So if this is Rx, so we can take interior from here or from here to express x as n plus epsilon or as x n minus epsilon. So if we take n here, right? So x can be written as this n plus this decimal part epsilon. So this case, and if we take n greater than x, so this is epsilon, and x can be written as n minus epsilon, which is this case. So in this question, we can write we are letting our x as n minus epsilon. Again, n is an integer and epsilon is between 0 and 1. Okay. So we are given as x plus m. So we can write x as n minus epsilon plus m, which is equivalent to again. Okay, so let's first write it like this, n plus m minus epsilon. Okay, so these are two integers, right? And we are subtracting some decimal part from this. So this gives us, we are taking the ceiling of this value. So what it gives us n plus m, right? So uh, this is r and this is m. So n plus m lie here, right? And if we subtract some decimal part from 0 to 1 from here, from this n plus m, this is r epsilon. So the ceiling, excuse me. So the ceiling of n plus m gives us n plus m, right? Because this is the closest integer which is greater than n plus m and less than all other integers which are greater than n plus m. Alright, okay. And we can write n as the ceiling of x because n is an integer, and whenever n we know that for an integer we can replace it with this function ceiling because it gives us n, right? Because we take x as n minus epsilon. The ceiling of x is, because since it is n minus epsilon, the ceiling of x is n, right? Because we are subtracting something from an integer, and when we are taking its ceiling, it gives us this integer. Okay, and plus n, which proves our desired result, i.e. ceiling of x plus m equals to ceiling of x plus the integer m. Okay, no. Okay, another question. The next question is question 51. Okay, so this is an interesting question and it requires a bit of work. Okay, so the question says is if x is a real number and n is an integer, then the part A says okay, x is less than less than n, this real number is less than this integer if and only if the floor of x is less than n. Okay, now since the statement comes with if and only if thing, so we have to prove it on both ways. So the first way, i.e. if x is less than n, then floor of x less than n. Okay, excuse me. Now let x is less than n, and since we know that floor of x is always less than equals to x by definition, right? And x is less than n, this implies floor of x is also strictly less than, because this thing is strictly less than n, right? From the hypothesis. Okay, so this is something like trivial. Okay, so the other way around, if floor of x is less than n, then x is okay. So the counterpositive of this statement is okay, counterpositive. I'm using counterpositive statement to prove it because this is very easy, as you will see in the next few lines. Okay, so what's the counterpositive of this statement? This is P and this is Q, right? So equation Q, which is x is greater than equals to n, then so if x is greater than equal to n, then floor of x is greater than equals to n. So this is the counterpositive statement. This is negation P, so negation Q, and negation P. By the way, you can use any proof techniques, right? Direct proof by contradiction or any other legitimate technique. You are free to choose any techniques to prove this question. Okay, now, so this is the counterpositive statement. So let x is greater than equals to 1. So what does this mean? This means that the greatest integer not exceeding x must be at least n, right? And this means the greatest integer, the greatest integer not exceeding x must be at least n. Right? And since since n is an integer which is not exceeding n, it implies that the floor of x is the greatest integer not exceeding x is greater than equal to n, right? So it's just a matter of definition when we write a statement in counterpositive form. Okay. So this is the proof of part A. The proof of part B follows by the same technique, so you can do it by yourself. Okay, so let's just do it. B, what's the B statement? That if n is less than x, then n is less than the ceiling of x. Okay, n is less than x if and only if n is less than ceiling of x. Okay, again, the statement comes with if and only if thing. So we have to prove it in both ways. The first take a forward way, i.e. if m is less than x, then n is less than ceiling of x. Okay, now let n is less than x, then by definition we know x is always less than ceiling of x, right? Less than or equal. Okay, and this is again greater than n, right? So this is one that n is greater than equals or less than equals to ceiling of x. Okay, because we take this as that n is less than x, and this x is less than equals to x, and since there is an inequality strict, so it remains just sorry for that. So this is less than 0. Okay, now prove the forward statement, backward statement, which is if n is less than x, ceiling of x, then n is less than x. Again, you can prove it by any technique. I am using counter-positive statement first and then prove the counter-positive and both are equivalent. So by proving counter-positive statement, we prove the original statement, right? Okay. So the counter-positive statement is if n is greater than equals to x, i.e. negation q, then negation, which is n is greater than equals to ceiling of x. Okay, so let the hypothesis, i.e. n is greater than equals to x. What does this means? We are saying that n and n is greater than equals to f, and this means the smallest integer not less than x must be greater than n, right? Oh, sorry, must be greater than n. Okay, now since n is an integer not less than x, what this implies? And it's greater than equals to ceiling of x. So that's the definition of ceiling. The smallest of all greater integer which are greater than x. Okay, so this concludes the part as well. Let's proceed further. And so our next question is so our next question is question 53. Okay, so what it says. Prove that if n is an integer, then the ceiling, the floor of n by 2 is equals to n by 2 when n is even, and the floor of n by 2 is n minus 1 by 2 if n is odd.